And then on top of that, global warming and desertification is adding to the problem. So if you look at this situation, a desalination of seawater seems to be a best option to tackle this problem. But unfortunately, desalinification is an expensive process. It consumes a lot of power. If you consider common system that used on board, like conventional system is evaporation of water and then at low temperature and then producing fresh water. But this process is very slow. When it comes to large scale, it may not cope up with the rate. And presently, most of the desalination process happens with RO. So RO is one of the most emerging technology. What seems to be coming up now. Reverse osmosis. I'll just give a brief what it is. Reverse osmosis. In this we use membranes, and we pressurize saline water on one side of this membrane. There is a tendency of water to have an equilibrium. So what happens? The fresh water has to flow because of this pressure, high pressure. Fresh water has to flow across this membrane, and then this is how the saline water and fresh water get separated. Though it's very easy to explain this way, but in actual the process is a bit complex. Latest nowadays we have got emerging technologies like PTRO and BOOT model. These are coming up as a better options. So today in this webinar, we will be discussing these innovative technologies, what they are, how they are, and how effective they are. We have eminent speakers to discuss on this topic. So before going into the topic, I would like to introduce our chairman for the Marine Division Board, Mr. B.M. Bhandarkar sir. He is IEI Marine Division chairman. He is basically he is an engineer who has been serving on INS Chakra. It's the first nuclear submarine operated by Indian Navy. He has been associated with many professional and social institutions. He is a board member of Asia Pacific Industrial Engineering and Management Society, Japan. And he is also a fellow of IEOM, USA. He has received many awards and honors, mainly Coal India Productivity Award, Lillian Gilbert Award, Jewel of India Award, Educationalist Award, Shiksha Bharati Puraskar, and the list is much bigger. So it would be better that we hear from his mouth. So I would like to welcome Commander Dr. Bhaskar Bhandarkar. So please address the meeting. Thank you.
Thank you, Engineer Mahesh. Respected Dr. Mohan Dagavkar sir, chief guest of today's function, and the dedicated officer from Institution of Engineers who has taken this great institution to greater heights with his dedicated efforts. Today, the Striving Navi Mumbai Local Center is the testimony to his vision, hard work, and dedication. I welcome you, sir, and thank you for this being present for moderating this seminar.
Thank you.
I welcome our MRDB member, Mr. K. Bindu Mohan, sir, National Council members. I welcome Dr. D.G. Mahajan, the stalwart, visionary, and technical mind in India, who is doing too good for the Indian industries in the international wage. I also welcome my friend, engineer Glenn Gonsalves, who is an environmentalist and a very successful engineer, and who is doing great contribution to the productivity of Roche. I welcome my friend, Honorary Secretary of Maharashtra State Center, Engineer V.C. Kamble sir. Whatever progress we see in metro today, he has got greater part to play in it. And another couple of years, many of will be thanking him for his vision, dedication, and hard work for making our life comfortable. I thank I welcome Mr. Mahesh, a faculty, a quality crusader from Samudra Institute of Maritime Studies. I welcome all the participants, distinguished members of Institution of Engineers and Institution of Marine Engineers, council members from Institution of Engineers, office bearers, dear students, and media person. As Engineer Mahesh said, we have got nearly 71% of water on board this blue planet. However, as we know, only 3% water is the potable, is being good for the human consumption. Thus, as our population grows and the pollution increases, the climate change is zooming on. The importance of availability of fresh water is much needed. Institution of Engineers, we are promoting new technology, new practices, and we have taken up climate change, global warming, scarcity of water, pollution on our hot list of topics to be deliberated and contribution to the society. Marine Division of Institute of Engineers is a vibrant one and putting a lot of efforts in promoting technology, bringing the good people on common platform and contributing our bit to create awareness. As you know, within the lecture of 1.5 hour, we cannot train you to the perfection, but we can put that chingari, that fire, that lamp within you so that you will be inclined to learn more and more. I wish this webinar a great success. The distinguished faculty are well acclaimed internationally, and I am sure we'll have much take-home content from this webinar. Thank you very much. Best wishes.
Thank you, Bhandarkar sir, for kind words and good wishes. Now I would like to introduce and invite Dr. Mohan Dagaukar. He is a chief guest and a moderator for this session today. Dr. Mohan was a former additional municipal commissioner of Navi Mumbai Municipal Corporation, former city engineer of Navi Mumbai Municipal Corporation. Basically, he is a civil engineer, graduated from Indore University. Then he has done his PG in environmental engineering from VJTA, Mumbai. Then achieved his PhD in civil engineer from the prestigious University of Nagpur. Professionally, he has served almost 36 years at Navi Mumbai for the Navi Mumbai city. He was a chairman and honorary secretary for Institution of Engineers Maharashtra State Center. He has been involved actively in various projects, such as construction of a very high capacity Morbe Dam at Navi Mumbai city, and it is still serving for next. It will be serving for next 20 years. In laying and commissioning of water transmission lines from Morbe to Navi Mumbai. Now it is providing 24/7 water. Development of SCADA system to monitor water pressure, water quality and quantity right from the dam to the distribution network. He has been involved in development of scientific landfill sites for waste processing unit. He has been working for a 500 bed general hospital, various buildings, including schools, mini stadium, fire brigades, community centers, and more. He is also involved in beautifying the city by developing various chowks, monuments. For example, the Shivaji Chowk at Vashi, beautification of and restoration of old lakes and visions. So he is the right person to talk about water consumption and conservation and harvesting. So I would like to invite Dr. Mohan Dagaukar to this forum and to take over the proceedings henceforth. Welcome, sir.
Thank you, Mr. Mahesh. And I welcome all the delegates and participants for the today's webinar. And to start our today's panel discussion, so I'll introduce our first panelist, DG Mahajan sir. He is the Vice President of ROChem Separation System, and he is a graduate of College of Engineering, Pune. And then he has done marine engineering specialization from INS Shivaji in 1989, and he served Indian Navy till 1996. So, and he has more credentials to his qualification and professional career. So, this is just brief introduction of Sri D.G. Mahajan, but when he will be discussing on this today's topic, we will come to know about his knowledge and his experience that he will share with us. So I invite D.G. Mahajan sir for today's his lecture.
Mahajan sir, before we start, I take this opportunity to welcome our former Vice President, Institution of Engineers, the Crusader of Quality and Technology, Engineer V.B. Singh sir from Lucknow. Now, please, thank you.
I welcome Sri V.B. Singh sir also. I was not knowing. So, V.B. Singh sir, you are also welcome. I also welcome all our MRDB member and most our chairman, Dr. Bhandarkar sir, because of his efforts, today's webinar is taken place, and he is doing all this technical work very effortlessly and continuously he is doing. So that also I'm thankful to him and welcome.
Yeah, Mahajan sir.
Yes, sir. Thank you, sir. Thank you so much for giving this opportunity. Respected dignitaries, Dr. Dagaukar, sir, I think we literally dote on you, sir. We follow you. Commander Dr. Bhandakar, sir, Mr. Kamble, and all the dignitaries on the diet. I thank you again. I just start the presentation now. Okay, can you see?
Yes, yes.
Okay. Here on the screen, I've just shared the slide wherein just some of the snippets of some of our clients. Many of our clients are basically they are listed companies, and as a part of their annual reporting and as a sustainability report, today it has become a mandatory to declare. So you can just see that these are kind of environment metrics that are being put in force, and also companies are actually reporting. Like one of the companies, which is our international client, they are reporting water efficiency, which is almost like they have been able to bring the consumption down to almost like 4.13. So another client, they have kept the environmental footprint for reduction, specific reduction in the water consumption. which is almost like they have targeted almost like 20% reduction, and which already they are already achieved so far specific water consumption. Another client where they have been able to even targeting even energy consumption, water consumption, also waste reduction, and the kind of activities or maybe the baseline activities what they are doing, like introducing a zero liquid discharge in their plants, implementing various technologies to reduce the cooling tower water consumption demand, and so on and so forth. And this is what maybe the industries are being made aware, and also they are being part of the environment, and they are also declaring that how they are able to achieve this kind of a reduction water consumption. And that, so you can see the kind of a word that is being used: water consumption, efficiency, footprint. So these become compulsory declarations by the companies, and which are listed. They should be answerable, or they should be responsible to the environment and ensure the sustainability report, which includes their commitment to the water and energy, all other footprints. So with this preamble, I will just move on to the presentation. It is a maybe a mix of presentation. It is some kind of a technical inputs and also some of the pictorial ones. So I will be just running the presentation with basically water availability, its importance, what is water stress, then water and wastewater treatments in maritime industries and others, and also ZLD, which is the total recycle. So what is water? Basically, water is colorless, tasteless, odorless, transparent organic fluid, a chemical substance known as a universal solvent. And the importance is basically it is for all the forms of essential for all forms of life. It covers almost 75% of the Earth's surface, and only small water that is available for the people. It's almost, as you can see here, almost only 1% of the water is available for the living things. And most of the water, 97% is in oceans, and 2% is frozen in the north and south poles and glaciers. So as you can see, the water stress across the globe, India is one of the most water stressed countries. And as you can see, the India's water stress is almost like 54% of the India is water stress. And even if you see the globally, the 1% of the fresh water available in the world, India holds almost 4%, and India represents almost 16% of the total population. So you can see the availability of the water per capita is very less. So the water stress is predominantly, it's basically a measure of withdrawals as a share of renewable surface and also the groundwater supplies. As you can see, in India, major water consumption is for the agriculture, as against the other part of the world. Europe is almost like kind of 33%, and world it is almost like kind of 68%. But for water consumption, India is one of the lowest water consumption per capita consumption, while as US is almost like kind of more than 15 times of India. So as you can see, the water demand is going to rise over the years, but definitely the kind of efforts that are being put in to ensure that water efficiencies or water consumption reduction or the water footprint, that will definitely ensure the water consumption will dip towards 2050, and that is a very welcome sign that we should be seeing it in the years to come. So just to take you through the membrane technology, I will just briefly show you what are the spectrum, the filtration spectrum, basically what all ranges that we have. So as you can see in front of you, the filtration spectrum almost starting extreme on your right, which shows particles which are visible to your eyes, and as you go towards left, the particles are not visible to the eyes, or as you can extreme left, you can see the atomic radii or metallic ions, aqueous salts. And so for various contaminants in the water, so as you can see, the various contaminants in the water do pollute the water, or they are a part of the various water that is being consumed for whether either for drinking or for the industry. So for removal of all of that, various filtration technologies are being used, or membrane technologies are being used. Our membranes are purely filters, or very high quality filters, which are being used for separation of these contaminants. So as you can see, the particulate filtration will remove what is on your right, basically beach sand. As you come to microfiltration, it will remove what is on its right. And coming to ultrafiltration, it will be removing most of the asbestos or some of the viruses, and most of the bacteria can be removed by ultrafiltration.
Right.
Nanofiltration is in between ultrafiltration and reverse osmosis, which will definitely take care of very specific ions, which are basically the monovalent or divalent ions, which it takes care. And while as you can see, extreme left, that is reverse osmosis, which is the extreme end of the filtration spectrum, which almost can filter out the metallic ions or aqueous salts or sugars, or it can remove an entire range of viruses or bacteria that can reject. So based on the membrane processes, what we typically these are used, we have a purification or disinfection or desalination. Desalination is a very higher form of purification. And for purification and disinfection, we can use microfiltration or ultrafiltration for river waters. But while as if you go for the saline waters or brackish waters, we need reverse osmosis or nanofiltration, for which is basically ion selective membrane, which will be able to remove. So these are the range of applications in desalination for membrane, right? Starting from seawater desalination, which is a very standard basic application for seawater desalination, coming to brackish water desalination or CT borewell water purification, industrial wastewater recycle, reusable water from wastewater is the major technologies that are being deployed by us in various industries. Sewage recycle, industrial grade reuse water from sewage. Landfill leachate, which is another major cause of ground pollution in across the cities. Ultrafiltration for biological membrane bioreactor, which definitely also is used in the maritime industry on the ships in the form of a biofilm, which I'll just be showing. Radioactive waste, wherein we are able to apply these technologies for minimizing the radioactive waste volumes, only extracting the pure water out of it and then only concentrating the radioactive waste on the other side. And dye concentration, ultra pure water. Effluent treatment plants, definitely biodigesters, and total zero discharge solution on EPC basis, which Rochem is quite having a strong hold in the industry. And waste heat evaporators, which my friend Mr. Glenn will be talking more about. So what kind of resources that are there, or even like although the subject was for the maritime industry, even like to start with, like on the ships we have gray water, black water, and also we have sea water on the outside for producing pure water. So the gray water or sewage water is the best option or resource, which is basically alternative for the fresh water, which can be used on the various locations for normal flushing, gardening purposes, which definitely can be used as an alternative resource. And seawater is abundantly available resource, which is available even in India. We have almost like a very big coastline, over 6,000 kilometers, it's touching almost 9 states, which definitely is a big advantage for India, where India is slowly moving towards seawater desalination, slowly but surely, for obvious reasons, because of the capital expenditure involved and also the energy cost of it, and also definitely the environmental aspects of the seawater desalination plants, which have to be mitigated during its installation. So the gray water, black water that is on the ships, what we basically that is collected from the various showers, bath basins or washing machines. This treatment on board ships is easier than the municipal wastewater treatment. And in this, for this reuse and recycling, typical applications for gray water recycling will be used. It can be used for toilet flushing and even irrigation across. If not on the ship, it can be on the ground. So we have some of the technologies called MBR or biofield based MBR technology, which basically combines advantages of the membrane and also its capability to concentrate the contamination, the biological contaminants. So as you can see, this is a very simple the representation of the biofilm, wherein you can consider this as a ship's the gray water storage tank, and what it has is basically a vent line, a process air that has been put in, and there's an influent coming in from various systems. And what we apply is basically this kind of a device here. There's a filtrate that is coming in from this treatment system. So if you see this is the conventional system that is there. Most of the conventional treatment plants have this kind of a aeration tank and a settling tank. They put some kind of a microorganisms in the aeration tank, and during the operation, some kind of a overspill or maybe carryover of the bacteria happen in the settling tank. They are basically recycled back, but there is also possibility because of the excess growth of microorganisms in aeration tank. There is a possibility of carryover in the effluent, and that is also one of the major reasons for the conventional treatment plants not working successfully elsewhere. So what we have is today the biofilm on the ship. So this has a hydraulic load dependent on the microbial growth rate, and also biomass concentration is uncontrolled. As you can see, it gets carried over, and also it can get completely washed out also in the process. While as you can see here, the biofilm application, we are able to use a ultrafiltration membrane module and able to retain the bacteria within the process itself, and we are able to increase the concentration many times over, as high as 3 times in the process, and we are able to only take the filtrate out, and that filtrate can be used as a alternative water for flushing on the ships also, because many of the ships today have a freshwater flushing, which this is a kind of a good quality water that can be used for flushing. So there is no bacteria, no microorganisms can pass through the membrane, and we are able to retain them and increase the process efficiency of the process. So this is the biomass concentration independent of the hydraulic load. This is controlled very well, and also it is a high rate system, and we are able to get good results for containing the microorganisms as against the conventional systems. So this is a kind of a flat membrane system, which is ultrafiltration, where we have a disc inside the membrane, and these membranes are assembled together. This form a cassette, and this cassette is basically like an exploded view of the cassette, where we can vary the gap between the membranes to allow the passage, and we can have multiples of these depending on the capacity needed on the ships. So as you can see, the flow that happens through the flat membrane module, which is the ultrafiltration module, we are able to get the feed flow and then basically the filtrate flow across the membrane. So this is one typical layout of a black water system on a ship, and also another actual photograph of a black water system. These are installed on most of the naval ships and also the submarines for handling the wastewater and minimizing the waste volumes. So you can see the kind of a filtration quality that you are able to achieve post this one, post the biofilm system. Another larger application that we are now applying this membrane bioreactor is basically being used for the sewage treatment plants. These are containerized sewage treatment plants wherein we are having an anaerobic pool, aerobic pool, followed by the membrane, and also the kind of a separate room, and all the pumping systems all housed inside a container. And this entire system can be portable, and it can be mobilized in a very short time. This is another view. You can just see this anaerobic chamber, and also the membrane bioreactor, which is being, and then the filtrate being coming out. So these can be very easy to deploy, plug and play kind of a MBR based compact sewage treatment system without any involvement of a civil work, which is normally a which is a norm in most of the sewage treatment plants. Now, further coming to desalination, now the membranes that we use, actually the ROChem has started with desalination to begin with, and today, as you can see, the desalination is a major industry and major technology that is being used for purification of the water, and RO has gained the popularity, as Mr. Mahesh also said, that it is only gaining the market share more and more, and most of the other technologies which are energy intensive in terms of their footprint and also the cost of capital and all cost of operation has really pushed reverse osmosis technology to come forward for supporting this desalination application and across the industry and also the world. So in membrane, in seawater membrane, we use 3 types of membranes, basically hollow fine fiber, spiral wound, which is basically double sheet, which is a conventional membrane, what we call, which has got a mesh spacer which separates the membrane and creates the feed flow path. And third one, what the ROChem uses is the plate tube type module, which we are using because of the very obvious advantages that it used. As you can see, the conventional membrane has very tight spaces wherein the water is not able to find the path, and that's why we take the path of this resistance. And over a period of time, this membrane gets choked, scaled, and fouled very severely. And this membrane is a factory sealed membrane, and it cannot be easily repaired or even diagnosed. So these membranes are kind of a thrown away as soon as the problems occur on this membrane. While as in ROChem split tube membrane, we are able to replace each and every membrane. Membrane and disc, these are stacked across the tie rod here at the middle, and we are able to identify even the defective membranes, and we are able to isolate those membranes or even remove the membrane and operate the complete module without a single membrane and get the output less by that membrane. So that kind of a modular construction and modular operation feasibility, this membrane technology is able to give, and we are the operators are able to continue the operation without even stopping the system. So this is a kind of a exploded component view. There's a disc and membrane, which are basically stacked on each other across the entire length of the membrane. You can see the complete length of the membrane along the tie rod. We have this disc and membrane, and disc and membrane, these are stacked, and we have this end flanges here, and this is the connection flange through which the feed water comes in, and it enters the membrane from here and passes over each and every membrane in series fashion. As you can see, as compared to this, the conventional membranes have a parallel flow and series flow. So because of which there is a greater chance of choking and scaling of the membrane. And that is what in membrane parlance we say this membrane needs maintenance or maintenance cleaning. While as in this kind of the membrane case, we are able to achieve a greater cleaning because the cleaner also take the path same which is followed by the feed water, and is able to lift the contaminants and scale and foulants on the membrane surface. And that is why we are able to get the membranes clean very quickly and very effectively. So this is a brief video how the flow through the membrane module happens. So seawater coming in here, entering the disc, entering over the surface of a membrane. Some part of the water passes through the membrane, and some part, the rejected part goes away as a reject, and it goes to the next membrane, and some part again gets purified as a pure water and gets collected in the middle. So as you can see here, the membrane is held in equilibrium. It is at the pressure, but although it is held in equilibrium, and there are no chances of any scaling and fouling. And as you can see, the suspended solids or even scale and the foulants which are held in the water body and carried away over the membrane surface very easily. And only we get some amount of scaling, which is basically taken care of with the chemical cleaning of the membrane or maintenance cleaning. So advantages of this membrane are really great, because this almost like kind of changes the performance metrics of the spiral wound membrane module to a very, very high level. So here, without with this kind of a membrane, we don't require all of that pre-treatment that is there in the system that is required for the conventional system, because they get choked and scaled very easily. The membrane that is used by the ROChem systems, basically plate tube module, they don't get choked and scaled easily. Here also we are able to do away with anti-scalant or dechlorination, and the system becomes that simpler with only pure coarse filtration followed by fine filtration. So the fine filtration part is only 10 micron as against the 5 micron in the conventional membrane modules, because of the passages are very, very fine in those membranes, while as in this membrane, the passages are very, very open and they are able to operate in open channel control. So these are the basic three advantages which we have summarized. The open channel feed flow path, the water is able to pass through very open channel and able to just get the permeation over the membrane right. Short flow path, because of the short flow path, we don't need to get the membranes to clean very frequently. Because of short flow path, the contaminant do not settle on the membrane surface, and minimal areas of no flow. There is not a single area where the water can remain stagnant, and the stagnant water can cause the scaling and fouling acceleration on the membrane surface, and that is where we are able to control the scaling and fouling of the membrane very, very easily on these membranes. So we have just expanded this technology of a plate tube module into various technologies. Like we operate with a spacer tube, wherein we have a very open channel spiral wound membrane, which are operating at a very, very high efficiency. We have a hybrid RO which are operating at various pressure, like 30 to 40 bar, and as you can see, the pressures are increasing, and at every pressure range we have a membrane. So this membrane technology is not restricted to seawater. So we are using this higher and higher pressure membrane in a very effective manner in our total zero liquid discharge system, where majority of the wastewater volume or reject volume of a previous stage is able to be reduced even further. And we have another two technologies, advanced DAF and waste evaporator, which also aid in overall efficiency or treatment process in the plant. So this is just a seawater desalination. As you can see, the conventional or maybe the open sea have typical TDS of 20,000 to 36,000. Although in near Gujarat it is almost 38,000 to 48,000, 40,000 almost. But from this kind of a salinity in a single stage, without much of pre-treatment, we are able to achieve the permeate of 500 ppm, which is the potable water quality. And also in the industries are using for various process requirements. So this is a typical scheme of a seawater desalination plant, consisting of the water taken from sea, passing through various stage filtration. This is a coarse filtration followed by fine filtration. And then here we have this device, which is basically energy saving device, which is called energy recovery system or energy recovery device, which saves almost 50% of the energy cost if this device is not used. So we are able to achieve almost recoveries, same recoveries as a conventional plant, but the energy consumption is almost 50%. And even in the same scenario, in case even if the systems are being used with the conventional technology and plate and tube module and with the energy recovery, ROChem, the plate and tube module systems are able to operate at a very, very high energy efficient system, because we are able to use the components which are very efficient. So as you can see here, the conventional 2,000 tons per day plant, like we can use the ultrafiltration system for pump, we don't require a pre-treatment or chemical pre-treatment. So even if you use this kind of a system, you will be requiring a power requirement of almost like 407 kilowatt for a 2,000 tons per day plant. While as the system with the plate and tube module, we are able to operate with almost 303 kilowatts of power, which almost like a kind of a the 25% reduction in the overall energy consumption even if comparing apple to apple in terms of the technologies, but in the core membrane technologies are different. And this is what is the advantages of membrane technologies kick in. And we have worked with various applications, even in the seawater, and we are able to now have taken them to the next level. Here we have a plant which have been operated on Podler. We operated 40% recovery. Here, which is we have an energy recovery device used, which is almost saving 50% of the energy cost. Here, another installation in the pharmaceutical, where we have given a system at 42% recovery. So almost like even like with the seawater salinity in Bay of Bengal is quite high as compared to the Arabian Sea. And here we are giving a high recovery. The system is configured very differently. Here we have another system which is in Run of Kutch, wherein the seawater or water salinity, feed water salinity is almost range of almost 42 to 45,000. And here we have given a recovery of almost 42% on the complete overall system. And this is where we our designing and also the component level designing and also the kind of a entire system build comes into play. This is another view. Now here we are using the very high efficient pump, which are almost like kind of a 90% efficient, and we are more using the motors of a high efficiency. So as you can see here, this plant which is installed in Goa, where we have a 50% recovery by use of again the component selection and also with the membrane technology for just kind of tuning the performance to the highest level. So this high pressure pumps have very high efficiency. Now coming to total, now I come to total zero liquid discharge solutions, wherein we are using this range of membrane technologies and also other technologies in the fold. We have anaerobic systems, which are basically the part of the system before beginning of any zero liquid discharge system. And we use various membrane systems. As you can see, the ultrafiltration, nanofiltration, reverse osmosis, and also we have ammonia removal system separately. Then reject of all of these membrane systems go into the waste heat evaporator, which basically remove again further good quality water and concentrate the reject. And that concentrated reject, which is taken into a crystallized drying or crystallized solution, which are basically drier than ATFD, in order to achieve the complete zero liquid discharge. So as you can see, there are various technologies in the play, and ROChem has a very good technology is being used at every stage that is being used, and that's why we are able to achieve the total zero liquid discharge at a very optimal cost. As you can see here, the ZLDs that are there in the vogue today in the industry, they have typical 4 stages. As you can see here, starting with pre-treatment, followed by physical chemical treatment, followed by ROs, and followed by the thermal treatment, thermal evaporation. So typically in the industry, as you can see, total distribution of the percentage of waste. Sorry. So as you can see, the 8% is almost used in the evaporation system, 2% is in the drying, 45% is in the evaporation, the effluent treatment plant, and 45% in the membrane recycling system. So this mix, this is definitely a kind of a initial mix. And in terms of the operating cost, the 6% is consumed by effluent treatment plant, 24% by reverse osmosis, 40% by evaporation, and drying cost, drying almost consumed for 30%. So as you can see, the major percentage is basically 40 and 30%. 70% costs are only in the drying and evaporation, which basically is a kind of a point which has been taken by ROChem in furthering the application. And today we are able to achieve 70% with, as you can see here in the typical cost distribution, 70% is with the fuel, and 25% with the electricity, and 5% for the maintenance. Okay, sorry. So I will be now introducing Mr. Glenn, who's our R&D head, who has been working on the waste heat evaporator system for years, and he will be able to take you through the waste heat evaporator system. Thank you.
So I'll just give brief introduction of Glenn Gonsalves. He has done B in biotechnology, and then he has done MTech in environmental solutions, environmental engineer, and he is having 12 years experience, having experience in study of standards and the technology solutions for treatment of um, potable water, ultra pure water, waste, oil, gas, industries, and desalination, fine chemicals, etc., and agrochemicals, desalination plants, ships, and others. So I request him to please give him uh, knowledge and experience by presenting his thesis. Thank you.
Thank you, Dr. Mohan. And thank you all the dignitaries for giving me this opportunity to talk here and present the data that we have. My colleague, Mr. Mahajan, has already taken you all through the process of water purification by reverse osmosis, I think in quite detail. But today the focus is on zero liquid discharge, because as he rightly mentioned, in a zero liquid discharge system, always the 70%, 60 to 70% of the cost comes from the RO rejects. So RO rejects has to be handled in evaporators and dryers. So basically, before going to the technologies that ROChem is working on or where the market is moving, I'll just present to you the technologies that are available today. So we have reverse osmosis, we have multiple effect evaporators, we have agitated thin film dryers for drying the final water, we have mechanical vapor recompressors, we have thermo vapor recompressors to increase the efficiency of the heating systems, we have evaporative crystallizers, and we have membrane brine concentrators. So this membrane brine concentrator is ROChem forte, because we have been extensively working here in this aspect. As Majan sir said, because of the cost influence on the water availability and water purification. So before going to any technology, there are some bases. So we just now saw about the different type of configuration of modules for reverse osmosis. So basically, reverse osmosis, the working pressure is defined by the difference between the reject TDS and the permeate TDS. Whatever is the permeate TDS required and the reject TDS that is achieved, divided by 1400 is the working pressure of a reverse osmosis system. So this is a basic fundamental for a reverse osmosis system. When we come to the evaporators, we have something called as gain output ratio. We call it GOR. So GOR is, and it is kg of condensate produced per kg of steam that is being used by the system. So in general scenario, when you want to evaporate 1 kg of water, you require around 1.2 kg of steam. So for a conventional single effect evaporator, you will require around 1.2 kg of steam to evaporate 1 kg of water. But in a multiple effect evaporator, now the third line mentions about MEE, multiple effect evaporator gain output ratio, is number of stages into 0.8. That's the efficiency. So today in the market, we have multiple effect evaporators up to 9 stages. So we can have a gain output ratio of 7 to 8. That means for every 1 kg of steam, we can evaporate easily around 7 to 8 kg of water. So that's how technologies are being used today to get efficiencies to the system and to reduce the cost of water for industries. Okay, and finally we have the agitated thin film dryer, which is working with a GR of 0.8. That's exactly what I was saying, that we require 1.2 kg of steam for evaporating 1 kg of water. So this similar diagram was there in Mahajan sir's presentation also. So we have the factories that is generating water, wastewater. Wastewater comes to the first primary physiochemical pre-treatment or the primary treatment. There it goes undergoes anaerobic, aerobic digestion if there are CODs. It only goes physiochemical reactions if it is totally inorganic salts, followed by the final the RO recovery units, wherein we have water being recovered. Around 90% of the water is being recovered by the reverse osmosis unit. Now remaining 10% of the water is not eligible for any disposal category, so it has to go to a evaporator. So we have a evaporator working here, and finally in this section, in this particular section, we have the dryer. So water has left the factory, it has passed through the physiochemical reaction, the biological reaction, then it has passed through RO permeate, or we can say the good water, the pure water is gone for the factory for recycling. The reject, the brown color reject is going to the evaporator. From the evaporator and the dryer area, again we have good water going to the factory, and finally we have the salts that are coming out of the Zereldi system. So this is how a Zereldi works. In Zereldi, the operational cost is basically 70% of the operational cost is because of the evaporation and the drying setup. Almost like 30% is from the ETP and the reverse osmosis unit. This is the breakup that we have generated, and this is the most, you can say, most efficient breakup of the energy utilization in a Zereldi system. And what ROChem does is ROChem and tries to ensure or reduces water for evaporation and reduces water for drying. So automatically you reduce the 70% of the cost to the customer. So ROChem always tries that, it has the reverse osmosis unit working at the highest possible efficiency and getting more water from a reverse osmosis unit, so that there is less water available for evaporation and drying, eventually reducing the cost of the water that is being treated. So today, after the basics that we have seen today in any Zereldi, if you see, there is a reverse osmosis. Again, there is a evaporator. It can be single effect or multi effect, up to 9 effects. There is a dryer and a crystallizer. So all the machineries or the equipment selection is governed by one single point, that is salt concentration of the wastewater. So for example, if we start with 1% of salt concentration, that corresponds to around 10,000 ppm of salt in water. So from 1%, we can go up to 10% in RO system, in conventional RO systems. So we can have a 90% recovery. So now around, suppose example, we take 100 liters of water and we have 1% of salt in it. We push it through RO, we get 90 liters of good water. Now 10 liters of water that is being rejected by RO, it goes to the evaporator. In evaporator cannot dry. Evaporator can only evaporate water to a certain extent, and that particular extent is 35%. Now this 35% is a very important number because this works around the solubility of the salt in water. For example, NaCl is soluble up to 32%, and there are various other salts which are soluble up to 40%, 35%, 32%, and there are techniques today available wherein you dose certain chemicals because of which the solubility of the salt present in the water can increase marginally. So this is being the conventional thing. So I'm just presenting the conventional thing here. So we go up to 35% in the evaporator, and finally around 3 liters of water that remains goes to the dryer. So we have 90 liters of water coming out of the reverse osmosis. We have around 6 to 7 liters of good water coming out of the evaporator. And finally, that 3-liter water that is remaining, it goes to the dryer. And we have around 2 to 3 liter water coming out from there also. And we have the powder. So dryer is essentially separating liquid and solids. Now the basic problem with this particular model is market needs low cost of ownership. Okay, and major cost being the thermal equipments in ZLD. So ROCEM aim is to reduce the size of the thermal equipment. So what ROCEM is doing about it? So ROCEM has its own waste heat evaporator. It's a plastic based evaporator. It operates on a low grade heat. It can be installed in a space constrained area like ship boards or any industrial setup where there is less area available. Corrosion problem is solved because it's plastic. We have maximum steam economy as compared to the conventional ME that is available in the market. And it can work on any kind of effluent because it is plastic. So plastic has a very rigid life as compared to any metallurgy that is available in the market. So that is how ROCEM is working on waste heat evaporators in the market. So same ZLD solution with a ROCEM approach. So we have a RO, okay, we have the evaporator, we have a plastic based evaporator. The only difference, ROCEM can go up to 95% of the up to 15% of the salt concentration. So that's around 93 to 94 liters of water can be taken out by RO. So automatically your 50% cost is reduced because the evaporator load has drastically reduced. So ROCEM takes the water from 1% to 15% in RO, from 15% to 45% in evaporator, as against 35% in the conventional, and then 45% goes to the dryer. So this is how ROCEM is solving water challenges and water cost for the industries. So because of this ROCEM approach and low energy approach, we can use integration to solve most of our problems. There is a lot of waste heat available in the market. So we can integrate it with the evaporators, okay, and co-generate water from the wastewater that is available in the industrial setup. Because we are operating on a lower temperature, we have lower scaling potential due to the lower temperatures. And because we are operating at a lower temperature, we have better condensate quality. So operating at a lower temperature in a plastic-based evaporator gives maybe 120 or 130% advantage to the conventional industry setup as compared to the industrial setup as compared to the conventional ZLD. So going ahead, the challenges that we face in day-to-day activities or day-to-day plant operations, we always term wastewater chemistry is always a mystery, because wastewater can come from any source in industry. Generally, in India, Indian context per se, the wastewater is not segregated well in industries even today. So we have wastewater, we have people dumping oil into the ETPs, we have some baths that are being drained into the ETPs without understanding what this bath or what this dumping will do to the ETPs that are in operation, and subsequently the recovery plants that are in operation. So this poses a very great risk for the plants that are operating downstream. So major challenge here, the NaCl, sodium sulfate, calcium chloride, calcium sulfate all have different solubilities. You can see here NaCl is at 32%, sodium sulfate is at 40%, calcium chloride is at 35%, and calcium sulfate just 0.35% soluble. So there is a wide range of solubility issue even in the water that is available for the system. So the basic challenge from a designing perspective is to understand the exact solubility of the salts that are present in the water or the wastewater that is given to the system. The second most biggest challenge is COD. COD, generally for the seawater, the COD is basically the marine life. It contributes to COD and BOD values. But in industrial setup, there can be any solvents in the system. There can be acetone, there can be hexane, there can be toluene, any recalcitrant chemicals that are not being treated in the ETP that can come to the reverse osmosis unit, to the evaporators and to the dryers. So this aspect has to also be taken when we design a system. Then going further, we talk about suspended solids. As Mahajan sir said in previous slide, he was showing about biofilm. So biofilm is nothing but removal of suspended solids or the biomass. So suspended solids basically lead to clogging of reverse osmosis unit or evaporators or dryers. So suspended solid is one thing that we always take care while designing the plant. Again, the pH value of wastewater. pH value, we are limited by the technology wherein we can use we can take water from 4 to 8 pH of range, or maximum say up to 8 or 9 pH, but the water can be available from 0 pH or up to 14 pH. So wide variety of wastewater is available in the market, but we can only take up to 4 to 10 maximum is the pH value that we can take for designing, and that is what I see as a challenge. Oil and grease. Oil and grease is again one aspect which is not taken into consideration during the designing phase, but we at Rochem, we believe that this is also very important parameter, and we take into design consideration because they have the tendency to foul the membranes, foul the evaporators, foul the dryers, and not allowing the solid to dry. So oil and grease also is one of the challenges in effluents that we are we are treating today. Then the energy cost. Energy cost will be the major driver for the entire project. So we were talking about technologies at our disposal, and we are looking today 10 years down the line where the systems are going, and we will be having some upcoming systems wherein we are looking at capacitive deionization, we are looking at carrier gas extraction, we are looking at biological membranes, we are looking at biological means of transporting water, and we are looking at freeze crystallization. So I will just brief you about what capacitive deionization is. See, we are looking at water as 99% and 1% of salt in it. So we are treating 99% of the constituent and leaving 1% to be there as such. So capacitive deionization works on that principle, and it treats 1%, and it doesn't treat the 99%. So that is how energy efficient capacitive deionization will be. Definitely there are challenges of electrode replacement, electrode scaling, electrode choking, but eventually we'll have technologies which we can overcome, and we'll be able to focus only on salts and not water. Then we have carrier gas extraction. So you all must be aware that hot, dry air, okay, is the best medium for carrying water. So hot, dry air is used to extract water, and again and in this process the air is humidified and it goes to a dehumidifier chamber, and the water is separated, and again the hot air is being recirculated in the system. This technology is just being developed, and maybe we'll have some plants or desalination plants in coming 5 to 10 years. Biological membranes. I believe that environment has all the answers for our problems, and biological membranes is one of that. We have the best membrane that is available in our kidney, which rejects salts, which rejects blood constituents selectively. So that is being done at 120 mm Hg of pressure, or you can say 0.16 bar. So we have the best membrane at our disposal in our body. So we are talking about biological membranes going ahead. Then we are talking about biological means of transporting water. Biological means in seawater, fish, in marine ecosystem, there are not many fishes. Okay, they be in the saltwater environment, but they never get affected by the salt because they have a mechanism in their system that selectively transport NaCl from one part of their body to the different part of their body, and keeping water intact into the body. So that is what I mean by biological mean of transporting water. So water transportation will be different from what we will be looking today. And finally, freeze crystallization. Freeze crystallization, you all must have heard about ice formation in Arctic circles or Antarctica. Generally, when ice is formed, the salt or the impurities are squeezed out of the crystal matrix, and the ice that we get out of the salt water solution is always pure. So we cool the water, seawater, we make it ice, and we separate ice and we separate salt. So this is freeze crystallization. This is done at around -30 to -40 degrees Celsius. There are pilot trials being done for this going ahead. So these are some upcoming technologies from what we conventionally have. So Rochem has been working in this space, and Rochem has this membrane brine concentrated as its prime product, and we have multiple effect evaporator in plastic base. So we are already tackling the water cost by adding this particular equipments in the system and reducing the cost of ZLD. And definitely we are working on this upcoming technologies going ahead for next 10 to 15 years. So just coming, I'll just end my presentation after this particular slide. So coming from a biotech background, I always wonder how things are working in our body. So as I mentioned in my previous slide, kidney works at 120 mmHg of pressure. That's equal to 0.16 bar, and we have a separation of 1000 ppm. Okay, so in reality, for the same amount of separation, we apply around 0.71 bar pressure, but in human body we apply only 0.16 bar pressure. So we are around 5 times away from what the biological body is doing today. We have the best diffusers in lungs. We have the efficient gas liquid mixing. Today, people are struggling to have good mixing in ETPs, good mixing in aerobic digesters, good mixing in anaerobic digesters. And we have the best diffusers, which are selectively working to take out CO2, nitrogen, and keeping in oxygen only in the body. So we have to learn from that. We have best piping system with minimal friction loss. We have 0.16 bar pressure in the body. Water can be lifted only up to 1.6 meters, but even a person with 2 meters height is living today. Okay, so the piping system in the body is with the minimal of friction loss. Okay, so we have to learn from the piping systems. Okay, and always we are facilitated or fascinated by what the West is doing. Only application studies in ZLD. They always tell us that, you know, you do ZLD by RO up to 10%, by evaporation, and then by dryer. But no, we don't have to follow them. We have to apply our brains. We have to go for fundamental research here. So I have just put one thermodynamic energy equation here. So when I dissolve NaCl, 0.5% of NaCl in water, there is an energy that is required. Okay, it's an endothermic reaction, and that energy is around 338.5 kilojoules or 0.003917 kilowatt per hour. Okay, so what I mean by this is, when you dissolve NaCl in water, there is some energy that is liberated or some energy taken out. So suppose, for example, if I give this energy back to the solution, the salt should come back, but it doesn't come back. So this theoretical energy is 0.00373917, and when we do the ZLD for this 5000 ppm of salt water, we end up having 0.56 kilowatts. So we are around 140 times away from the thermodynamic theory. So that is what we have to achieve as young brains, and that is where we are heading in Rochem. And how we are looking at water eventually the prices of water will get down, but water being a universal solvent, we see a lot of potential in having a lot of resources coming in water. For example, sewage in India today, the measured sewage or the treated sewage is 31,000 mld, and 31,000 mld is having around 15,000 tons of ammonia in it. And this ammonia, people are talking about green hydrogen and green ammonia and hydrogen stored in ammonia form. So we'll be having energy from wastewater, and we are seeing water as a source of carrying energy from one place to another. That's how Rochem is working on all the possible ideas for wastewater. With this, I conclude my presentation. Thank you, sir.
Thank you, Mr. Glenn Gonsalves. And we have we have listened both the learned speakers uh, lectures on wastewater treatment, in particularly on ship, how they treat grey water, wastewater, and particularly seawater. So, Mr. D.G. Mahajan and Gonsalves, both Mr. Gonsalves, both have uh, thrown light on how do they do this on ship, because when in ship there is those ship is traveled on sea water, but there is scarcity of water, so they have to utilize each and every drop of water. So they treat all grey water, they treat all wastewater, and they treat the seawater for their utilization. And for that, what technology they use, how they use membrane technology, how they use RO, and what are the challenges, and how they overcome it, and particularly in ROCAM, how they have tackled in all over India and in other parts of country also. And they have also thrown light that what are the upcoming challenges, and they have very beautifully told how much efficiency is consumed in drying and evaporation, and for treatment it is hardly 30%. And that too, Mr. Mahajan told that we have fantastic 7516-kilometer coastal line where we have to do only salt separation from the seawater. So this is a very big source of availability of water, but they both have gone into the economics of this also. That today it is very costly, but through ROCAM, in ROCAM, they are working on that, how to come up with more new technologies and how to overcome with the expenses. And from their detailed experience, because they have worked on this thing, it is not only theoretical, practically they are doing this thing. And from that we can learn that we can consider our cities like a ship, and consider that we are also having water scarcity. So if we can also treat each and every drop of our wastewater, our grey water, then we need not have to go to up to sea, but definitely treatment of grey water and treatment of wastewater is quite easier in terms of economy also, in terms of technology. So that thing we can take up with this. And with this, even actually, I forgot to welcome our Honorary Secretary, Maharashtra State Center, Sri V.C. Kamble sir, who is very energetic, very dynamic, and he is always with all the technical activities. It may be from Maharashtra Center or it may be from Navi Mumbai Local Center. He is always with us, and he is very enthusiastic in arranging all these things. So I welcome him also. And with this, because we are not expert in this field, the zero liquid discharge also, they threw light on zero discharge, liquid discharge, how 70% energy is consumed into that, and how it can be also. And Mr. Gonsalves has given us very beautiful example of biological membrane, which exists in human body, which exists in fish, and how it works, like kidney, our digestion system, our metabolism, our liver, and all these things. So that example also he has given, and they are also working on that. And I'm hopeful that something new thing will come, which will make more efficient, more cost effective, more energy effective solutions for treating saline water and our wastewater. So with this, I request our participants that they can be more enlightened by asking some questions to our learned speakers. So I think those who are interested, they can just ask, or our speakers can just go into the question answer box. If there are some questions, they can answer it. I think there is no question, but if somebody wants to ask, we have 5 minutes for that.
Dr. Dagavkar, sir, some of the questions that were asked by the participants, we have already answered one to one, sir,
Okay.
on during the course of the seminar itself.
Okay, sir.
Mr. Mahajan,
Yes, sir.
you have answered, And for the benefit of larger community, we can re-answer this openly so other people will be benefited, please.
Okay. So the first question was basically from Mr. Sridhar Bhalerao. Could you share some figures for desalination capacity like capital cost, operating cost, recovery, maintenance costs, breakdown issues, etc. This will give us some perspective on the subject of desalination specifically. So I've given basically the capex for the 2 MLD 2000 tons per day seawater desalination plant is approximately 7 to 8 crores. And operating costs are almost like 23 to 25 rupees per KL. Subsequently, Mr. Bharera again asked whether it includes what all it includes. So it includes basically chemical consumables, all the cartridge filter elements, all wear part, air parts, all shaft seals for the pumps and all of that is included in the operating cost. Recovery can be higher, 40 to 45% also. We are, as of today, we are demonstrating almost 50% recovery system. And as membrane, as Glenn said regarding the membrane contactors, wherein we are going much higher in terms of the recovery. So next question from Mr. Bhalerao again, that whether it includes the cartridge filter replacement, power cost also, and power and manpower cost. So the power cost is approximately the power cost, you can just consider the power consumption almost at the rate of 3.3 kilowatt hour per kiloliter of water produced. So if I produce 1 kL of water, I will consume 3.3 kilowatt power averagely in a medium sized plant or smaller sized plant. If you go on a bigger sized plant, it can come below 3. It can come less than 3. So even if you take a power cost at say 7.5 rupees per unit or per kWh, so the power cost almost can be almost like kind of a 15 to 24 rupees per KL of water produced. And he has also asked, what about the maintenance of the equipment? The maintenance of equipment definitely gets covered in the operation maintenance cost only. Then we have a question from Mr. Ashok Ghosh regarding what to do with the reject from RO membrane. I assume that this is a question related to seawater RO, but I've also answered in both ways. The seawater RO reject is typically sent back to sea as a brine. In a smaller plant, it gets mixed with the seawater, in the larger seawater being a larger body. In the larger site desalination plant, what we do is we install diffuser in the underwater on the sea floor, and the diffusers are actually pushing the water into the sea with the brine that is reject from the RO plant at a specific angle and at a pressure, and the water gets diffused in the seawater strata over a larger space. So those diffusers are used typically in the seawater desalination plant. In the ZLD scenario, we use the one RO reject for the next RO input. So we have a series of ROs in sequence, and those ROs, one RO takes the reject of the previous RO, and then so on and so forth. So we have almost 3 to 4 stage ROs in sequence in ZLD scenario. Next question was from Mr. Sridhar Bhalerao again. That is regarding the seawater TDS at the rate of at almost 40,000 milligram per liter, that is 40,000 ppm. Recovery 45% is feasible. That is what is the question. So I've replied that yes sir, we are demonstrating already with a 50% recovery with almost like 45,000 ppm TDS. So already in the run of Kutch, we are already demonstrating to a client. Next question was from Mr. Ashok Ghosh again. How to economize on the power consumption? What is the average power consumption for 1 cubic meter of treated water? So again, I've given him reply for seawater RO, the consumption is 3.3 kilowatt hour per KL of water produced. For higher capacity, it can come below 3 kilowatt hour per KL of water produced. Next question was from Nikhilesh Kamisetti.
Yes, I think it was for me.
Yeah,
So yeah. So basically the point that I was trying to make was, see, for every 1 bar pressure, the water can be lifted up to 10 meters height. Okay, so our body works with 0.16 bar pressure. So technically, the water should be lifted only to 1.6 meters. Okay, but today people who are 6 feet and above, they are also alive because the water is being circulated in the body. So why it is being circulated? Because of the minimal friction losses, because of auxiliary muscles being working. So these are all the things that we should learn today. The power factor, what Mahajan sir was talking about, that 3.3 kilowatt per KL. Okay, it is not only the power required to overcome the osmotic barrier of water of salt water, but it is also the power that is required to overcome the friction losses in pipes. Okay, friction losses in modules. So there are a lot many losses that contribute to this higher. See, today it may seem very minuscule, but when we are equating water prices with what is actually available to the people. Today, water is available for free in India, and we are talking of 8 paisa and 10 paisa per liter, but that's also expensive in industrial standards. Okay, so that is the reason we have to minimize even this particular losses, and we have to learn from our body how our body does it and how nature does it, so that we can deliver systems of tomorrow.
Mr. Gonsalves, Mr. VB Singh sir has asked one question, whether solar energy is used for in ship for treatment. So if somebody can just give the answer.
Sir, I will just like to answer. So yes, solar energy is being used. Okay, it is used in various forms basically. So solar energy directly for evaporation and condensing the water is one form of the energy. The second form is the conventional that is available in the market. You generate electricity, and that electricity operates the water purification plant. So your technically your power cost becomes zero, and you operate on sun. So that is how today in the market ZLDs are being done, and that's how today things are working, sir. Hope
Just
I
to tell
answered the
it,
question, sir.
Thank you. Thank you. Thank you, Majan sir and Gonsalves sir. And now I request uh, Mr. Vijay Kamble sir to give to proceed further. Thank
Yeah, thank you very much, sir. And really, it is very interactive and informative session organized by the Marine Engineering Division Board of the Institution of Engineers. And the main person behind this is Commander Dr. Bhandarkar sir. He is a member of Marine Engineering, Chairman of the Marine Engineering Division Board, the IEI, and he is instrumental in making this Marine Engineering Division, though it is a very small in magnitude, but technical activity wise, it is the biggest one in this institution, IEI. So a big compliments to Commander Dr. Bhandarkar for arranging this lecture, as well as updating the knowledge of all the participants who attended this program. So thank you, Commander Dr. Bhandarkar sir. The main person who is the chief guest of the today's function, and he is a moderator of the function, Dr. Mohan Balwan Dagavkar sir. He is a environmentalist. He done his post-graduation in the environment. He completed his PhD in the environment field only, and he executed many environmental projects along with all the infrastructure in Navi Mumbai city. So he is the perfect choice as a chief guest of the today's function, and in his busy schedule also, he take out the time and grace the function. So thanks to Dr. Dagavkar sir also.
Thank you, sir.
The main persons who, because of them, this knowledge sharing took place here, and the most dynamic name amongst them is Dr. D.G. Mahajan sir. So thank you, sir, for giving beautiful lecture on the subjects. You have explained the various methods, procedures of the treatment of the gray water, black water, and saline water also. You have unfolded all the insights of the treatment and explain all the data details as well as the various animation videos and figures also. So through that, all the participants really, they must have got through the whatever the message you want to convey. So it is really, we grasp that and we got whatever the information you have provided to us. So on behalf of all these participants, I sincerely thanks, and also on behalf of this IEA. So thank you, Majan sir.
Thank you, sir. Thank you, sir.
The second person is next in command in Rokem. He is a head of R&D in Rokem separation system. So he has explained innovative solutions in zero liquid system. He explained various systems available for the membrane technology and also solving the water challenges. He has explained the upcoming technologies and also given thought that if nature can do the miracles and we are 140 times away whatever the latest technology available in globally. So even though we could not match that miracle of the nature, so our targets, we should go nearer and nearer to the nature. So definitely all the participants and the young generation who are attending this webinar will take your thought and they do something which will be ultimately beneficial to the environment and the mankind ultimately. So thank you, Mr. Glenn Gonsalves.
Thank you, sir.
Nice. He is a marine engineering faculty come coordinator of Samudra Institute. He opened the seminar. So thank you very much, Mr. Maheshji.
Thank you, sir.
Also, Mr. K. Bindu Mohan is a marine engineering division, IEI, who is also graced the function. So thank you, Mr. K. Bindu Mohan. And one of our senior member of this IEI family, he is council member and he is a past vice chairman of the IEI, and he is a learned person who definitely gives some inspiration to us also. So engineer VB Singh is present for this webinar. So thank you, VB Singh. And the person who is coordinating all this seminar, webinar, and he is running to make the program successful as requested by or directed by Commander Dr. Bhandarkar sir. The person do all the background and he never come at the front, only his name we can see. He is a Mr. Kingshuk from IEI headquarters. So thank you, Kingshuk ji. All the distinguished members, corporate members, council members, and all participants and students who are present for this webinar. So unless and until there is a participants in large number, no program would have been successful. So big thank you to all the delegates who attended the program and enlightened with this knowledge given by Majan sir and Gonsalves sir, and nicely summed up by Dr. Mohan Dagaukar sir. And ultimately, Commander Bhandarkar sir, because he is taking lot many pains, and if all the getting benefit out of it, definitely his purpose of organizing this seminar will be definitely successful. So thank you all for this webinar and IEI for sparing the knowledge and dissipating the knowledge amongst the engineers to achieve the objective of the IEI. Thank you very much. Thank you all.
Thank you, Engineer Kamble sir, for taking out valuable time out of your very busy schedule. We are aware of that. and helping Institution of Engineers and MRDB to achieve our goals successfully. With permission from Dr. Davokar sir, we are left with few minutes. So there is one question pending about the use of plastic in RO industry. May I request Mahajan sir to kindly share his vision on this so we can utilize our time also.
Yeah, I think the question is from Chirag Pathak. Okay,
Yes.
so I have answered him. The question is plastic material solves for corrosion, scaling, etc. for RO reject systems. Okay. So, however, equipment used for transporting water is also made from plastic. Yes, it is. For example, our pipes and all are PVCs. Okay, UPVC, PVC, PPH, that's polypropylene. Okay, and because we are using plastic and because we are using it in RO reject, which are more concentrated, this concentrated have a very less impact of corrosion on this particular material. That is how we are solving problem of scaling corrosion in our systems.
That was there in your presentation also.
Yes, yes.
Yes, sir.
So with your permission, we'll end the webinar, sir.
Sir.
Okay. Kinshuk ji. Mr. Kinshuk. Hello. So we can call it a day. Thank you very much.
Thank you, sir.
Thank you. Thanks to all. Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you and good night, everyone.
Good night.
Right, Maiji.